Hello and welcome to our second tutorial in trigonometry. This tutorial is going to focus on using trigonometric functions to calculate angles of right triangles. In previous courses you've probably seen these trigonometry functions, sine, cosine, and tangent, and I'm hoping by the end of this tutorial I'll refresh your memory of what these functions mean and how we can apply them to biomechanical problems. In general, these describe the relationships of ratios of different lengths of different sides of a right triangle. So let's show these relationships. We've got our right triangle here on the bottom of the screen with an angle alpha shown. The sine of this angle alpha is going to be equal to the opposite over the hypotenuse, or in this case, the length of A over the length of C. The cosine of our angle alpha is going to be equal to the adjacent side over the hypotenuse, or in this case, our length B over our length C. Finally, the tangent of our angle alpha is going to be equal to the opposite side over the adjacent side, or in other words, A over B. It's important to remember that these tangent alpha, cosine alpha, and sine alpha functions are unitless. And an acronym to remember these relationships, which will be useful when applying these trigonometry functions in class or on an exam, is SOHC, where you take the first letter of all of these words. Sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, and tangent is equal to opposite over adjacent. So let's try and apply SOHC to an actual biomechanical problem. A golf ball is hit with an initial velocity of 30 meters per second and is hit at a 15-degree incline over the horizontal. What are the horizontal and vertical components of this velocity vector? A lot of times in this class, especially early on when we're talking about projectile motion, I'm going to be asking you to take vectors and turn them into horizontal and vertical components. So let's take this vector with a magnitude of 30 meters per second and an angle of 15 degrees, and let's solve for the horizontal component Vx and the vertical component Vy. To begin, we need to, when we're working with trigonometry functions, we often have to work in units of radians rather than units of degrees. So let's convert 15 degrees into radians. So 15 degrees, it's going to be equal to, and we multiply, by the ratio of pi radians over 180 degrees and when we do this, we get that this is equal to 0.26 radians. Next, let's solve for the horizontal component Vx. We know that cosine alpha is equal to its adjacent side over its hypotenuse. And we can rearrange this so that the hypotenuse multiplied by the cosine of alpha is equal to its adjacent side. In this case, our hypotenuse is our initial velocity vector of 30, and we know alpha from the problem statement is 0.26 radians. And we're going to use that to solve for Vx. And if we solve this equation, we find that Vx is equal to 29.0 meters per second. Similarly, we can show that the hypotenuse multiplied by the sine of alpha is equal to the opposite side using those trigonometry functions on the previous slides. Or in this case, 30 sine 0.26 is equal to Vy, or in this case Vy is equal to 7.8 meters per second. So this gives an example of how we would break down a vector with a known magnitude and direction and solve for its horizontal and vertical components. We can also calculate the angles within this right triangle by using inverse functions, where if we know the lengths of the sides, we can use these inverse trigonometry functions to solve for the angles within the right triangle. So we know that sine alpha is equal to the opposite side over the hypotenuse. If we take the inverse of this equation, we find that the inverse sine function of the opposite side over the hypotenuse is equal to alpha, our angle. You might see this shown as either an inverse to the negative first power, or you also might see these inverse functions shown as arc sine. Similarly, we can do the same thing for looking at cosine, where alpha is equal to the inverse cosine of the adjacent side over the hypotenuse. And similarly, tangent can be, you can calculate the inverse tangent function in order to calculate alpha as a function of its opposite and adjacent lengths. So let's try out one more example, this time where we're trying out these inverse functions to try and solve for an angle. So a baseball player wants to know the minimum angle they need to hit a line drive off of their bat to clear a 12-foot fence in left field, which is 368 feet away. So what is this minimum angle? So first of all, let's draw a triangle. Let me draw my pen out here. So we know that the horizontal distance the ball has to travel is 368 feet. And we know the vertical distance the ball needs to travel is 12 feet. And in this problem here, we're trying to solve for this angle alpha. So we know that the tangent of alpha is equal to its opposite side over its adjacent side. Similarly, we know that alpha is equal to the inverse tangent of its opposite side over its adjacent side. So here we're going to plug in our parameters, where we know that we're going to take the inverse tangent, excuse my pen here, and we're going to plug in the opposite side, which is 12, over the adjacent side, which is 368. And if we do that, we find that alpha is equal to 0.032 radians. And if we convert radians to degrees, we would find that alpha is equal to 1.9 degrees. So let's think about this. Does this answer make sense? 1.9 degrees is obviously a very small angle to hit a ball off a bat, and the reason why is in this simplistic problem we're ignoring things like the effects of gravity, the effects of gravity, the effects of air resistance, and that's why we're taking this course, is to really begin to appreciate the biomechanics and the relationship with the environment around the baseball player and how that affects their ability to hit a ball over a 12-foot fence 368 feet away. So in the simplistic case, we found that 1.9 degrees is the angle, but when we start to begin to account with projectile motion, the effects of gravity and air resistance, we'll probably find that this angle needs to be much larger. So in this tutorial, we talked about tangents, cosines, sines, functions, these trigonometric functions, as well as their inverse, and how we can use them to calculate the lengths and angles of a right triangle. In the final tutorial, we're going to begin to look at what happens when we have a triangle that isn't a right triangle. How do we calculate the lengths and angles of that triangle? I look forward to seeing you then.